Uh, Good evening, everyone. This is the NPTEL problem solving session for the course Introduction to Robotics. Uh, this is the problem solving session for week 5. And in this week, you have studied about mostly um, the structure of DC motor, basically how it is made, how the torque is produced, and all that. So we'll be doing just some very basic problems related to DC motor, and these will also help you in the assignment of this week. So let us just get right into the questions, and then you can, if anybody's there in the meeting, then they can ask some questions if you have. Okay, so let me just read out the first question. Okay, so that is a rectangular coil of length 15 centimeter and a width of 8 centimeter is placed in uniform magnetic field of flux density 0.8 Tesla. So such that the plane of the coil is at an angle of 45 degrees to the direction of field. Okay, now we have been given that the coil has 20 turns and it carries a current of 5 amperes. Okay, what is the torque experienced by the coil due to, of course, this magnetic field? Okay, because we know that if a current carrying coil, is basically if a current carrying wire is placed in the, if this is a current carrying wire, if it in the vicinity of some, magnetic field, okay, then this wire experiences a torque. So if you have a loop like this, okay, so basically like this coil, okay, so it is saying that it has a length of 15 centimeter and then it has a width of 8 centimeter. Okay, so basically it will experience force or essentially a moment on it. Okay, and the moment will be generated because there are forces on both the arms in the opposite direction for this coil. Okay, because the direction of current in both the arms is opposite. Okay, so there will be a net moment, created on this coil because of these forces. Okay, and then again, we have been given that there is a magnetic field. Okay, so let us assume that this is the direction of the field. Okay, and then this is the perpendicular, to the, this is the plane perpendicular to the direction. Let us just assume I'm trying to draw the plane perpendicular to this, magnetic field. Then there is, our coil is at 45-degree angle to this. Okay, so essentially if this is our coil, okay, if this was our coil, okay, then, and if this is horizontal, okay, then our coil is essentially making an angle of 45 degree. Okay, and let us say that in the vertical there is your flux, okay, magnetic flux. Okay, so I think you have not, you have studied about these kind of situations, like force on a current carrying conductor and the torque on a loop, current carrying loop, basically. How do we calculate it? Okay, so this expression that you guys have seen and the derivation you have, seen in the lectures is this, that the torque is equal to the, I'll just write and then I will explain. Okay, that what are all these quantities. Sine beta. Okay, so this result, of course, this is for a rectangular, you know, coil with multiple turns. So basically, N here is the number of turns. Okay, number of turns. And okay, and this was given that it is 20 turns. Okay, it is given in the question. Okay, B here. Okay, B is the flux density that I have represented by phi. Okay, so B is your flux density. Okay, and it is given in Webers, right? Weber is the SI unit of flux, magnetic flux. No, Tesla. Sorry. Okay, so this is given you as pointed Tesla, right? The flux density is pointed Tesla. And then you have your current, okay, current in the coil that in the future we'll call it armature current, but we'll discuss it when we come to that kind of question. Because this for now is just current, that is current in the coil. And how much is it given? It is 5 amperes. Okay, and this L and W are the length and width of the coil, because I told you, right, this result is specifically for a rectangular coil. Okay, so L and W are the length and width of your coil. Okay, and how much are they given? Length is 15 centimeter. Okay, so 0.15 meter, and it is 8 centimeters, so 0.08 meter. Okay, I'm just trying to keep everything in SI units. And then what is beta? Okay, so your beta is the angle between your flux density, or basically your magnetic field, and your coil. Okay, so basically what is the angle that the coil makes from the direction of the flux density. Okay, in this case this is given as 45 degrees. So essentially in this problem you just have to take all these values, plug this in the formula, and then you'll get the final value of the torque that is there on your you know coil. Okay, so let us do that. So this is 20 times 0.8 times 5, and then 0.15 times 0.8 times sine 45, right? So 1 over root 2. Okay, so this comes as what? 5, and then okay, so let me just quickly do the math for you. Okay, so if you guys do this on your own, then what you'll get finally, okay, you'll get approximately 0.125 Newton meters of torque. Okay, this is the final torque that you'll get. Okay, so basically for the given coil with 20 turns, the given length and the given width, and at this particular angle, in such a field, in such a magnetic field, this coil will experience a torque of 0.125 Newton meter. Okay, so this is like a pretty straightforward question. So let us move to the next kind of questions. Okay, let us, this is Q2, right? So I'll just read out the question and then we'll solve it. The question is a rectangular coil having, again, it is a question of rectangular coils that we have seen above, having length of 15 centimeter and a width 8 centimeter and 20 turns, is displaced in a uniform magnetic field of flux density 0.8 Tesla, such that the coil sides are perpendicular to the direction of field. Okay, now this is important. Okay, so we have been given that the coil side is perpendicular to the direction of field, right? So what does this mean? Let us say that this is the direction of the field. Okay, then the coil sides are always, like, I think we placed it like this only in the last question also. Okay, they are always at 90 degrees. Okay, so basically your coil is rotating such that the sides are always perpendicular, to the flux magnetic field lines. Now, if the coil is manually rotated at a speed of 1000 RPM, right, such that the axis of rotation is perpendicular to the direction of field, right? And we have drawn it to be perpendicular here, right? Because it was kind of implied also, given the other information. Okay. Now we want to find the peak value of EMF, basically the electromotive force, or what we also call it, the back EMF, developed across the coil. Okay, so basically if you are manually moving the coil, manually rotating the coil at this given speed, at this given orientation, okay, what is the value of EMF that is developed across the coil? Okay, so here also for the solution, you know from your lectures that the EMF, okay, or the back EMF is given as, okay, the expression for back EMF is 2NBLR times omega, right? So like there is, okay, and the derivation of this you have already seen in the lectures. Okay, and if you do not recall what this is, I encourage you to watch the lectures again because it is explained there pretty much. So we write all the quantities that are given to us. Okay, so n equal to 20 turns, it is given. Okay, and the field magnetic, flux is 0.8 Tesla, that is also given. And your L, right, your L is what? L is 15 centimeter. And then we want R. Okay, but what is R? Okay, so R is the radius of coil, right? But what is exactly the radius of coil? If I assume that this coil, that my coil is a circle, okay, it traces out a circle, okay, then what is the radius of this circle? Okay, so basically this width, this complete width of my coil, okay, becomes the diameter of the circle, and that is, R by 2. No, the diameter is what? 2R, right? So now what is the radius of coil? It essentially comes out to be width over 2. Because in this case also, the radius of coil is width over 2. And what is it? 0.08 meters, right? So the radius of coil comes out to be 0.04 meters. And length in meters is 0.15 meters. Okay. And then what is omega? Okay. So omega is the speed of the coil, but in radian per second, right? And right now it is given to us in what? RPM. Okay, so how do you convert from RPM to radian per second, right? So the standard that you multiply by 2 pi, because one full rotation is 2 pi radians, and then you divide by, you convert minute into 60 seconds. Okay, so what you finally get here is your speed. Okay, so and that is 100 over 3 pi. Okay, you can solve it further, but we will solve it towards the end. Okay, so now you have all the quantities that you need to calculate the back EMF, right? And this is the expression for back EMF. So we just plug it in. Okay, so E is your 2 times 20 times 0.8 and then 0.15 cross 0.04 and then omega. Okay, omega is my 100 pi by 3. Okay, so now if I just, if you do the complete calculation, I think yeah, I'll leave it up to you to verify the calculation. I will just, yeah, so this, this will become 4 and this will be pi by 3. So when you solve it completely, you will get back EMF as 20 point, what is it? 106 volts. Okay, EMF. Okay, so this is the voltage that you will measure if you try to measure the voltage at the terminals. Okay, the two terminals of the motor. If you try to attach a voltmeter here and then you rotate the coil by the given omega, okay, then the voltage that will show up in this voltmeter is, and that if that omega is 1000, then that voltmeter will show how much? 20.106 volts. So basically this is how you calculate back EMF for a given coil, that is approximated as a rectangular coil, right? So I don't think we you guys will have any problem till now. If you have, you can just stop me and we can discuss, right? So now let us move on to the next question. Let me mark it as question number 3. Okay, so this question is, now we have moved from our rectangular coils to PMDC motors. Okay, so like you all know, right? The only difference between PMDC motors and brushless DC motors is in the pattern of their back EMF. Okay, so for brushless DC motors, the back EMF is, the back EMF profile is trapezoid. Okay, for BLDC motors, but for PMDC motors, okay, the back EMF profile is actually sinusoidal. Okay, so that is actually, many people say that BLDC and PM, PMSM motors are the same, but like they're not. There is this difference in the profile of their back EMF. I think what I told you is true for PMSM motors. Okay, and right, I don't think we are talking about PMSM motors right now. We're just talking about PMDC motors. These are permanent magnet DC motors. What I told you is true about for permanent magnet synchronous motors that you will learn about in the next week. Okay, so in a PMDC motor, if the armature is rotated at 100 RPM, an EMF of 5 volt is developed across its terminals. Okay, so it is similar to what we did in the last question. Okay, so now for this motor, we want to know what is the magnitude of armature current flow required to generate a torque of 0.5 Newton meter. Okay, now you can see that this question is actually a combination of both the questions that we have done above. Okay, how? In the first question, we had been given the magnitude of armature current and the other quantities. Okay, and we were required to calculate the torque. Okay, and in the second question, we had been given everything else and the RPM, and we have been asked to calculate the EMF, right? Now, in this question, we have been given, RPM and the corresponding back EMF, but we have been not given the other quantities of the rectangular coil, namely the length and the width and the field, right? The field strength or the magnetic field flux density for the given arrangement, and we have been given the required torque. Okay, so we want to know that how much current should I pass, through this coil to get this much torque. Okay, so basically we'll have to use both the formulas that we have seen above, right? So like we can also use both the formula. So the first formula that we saw was this, right? NBILW and then sine beta, right? And again for E, we knew that it was similar, right? NBLW. Okay, this is also my W and this is omega sine beta. Okay, because here we did not write sine beta because we have been given that these are always perpendicular. Okay, so now if I say that that everything else is constant. Okay, what everything else? This NBL omega, because these are properties of your NBL sine omega and this sine beta. Okay, like this beta is constant actually. Okay, for this arrangement, beta is 90 degrees. Basically, you can put these as one. Okay, so what you get is basically an equation like this. Your tau is K times IA, that is your armature current, and your E back EMF is the same K times omega, right? Okay, and now you can see these are like the same constants. Okay, now when you uh, go to see the motors, okay, you'll see two coefficients or two constants that are important. One is the current rating and one is the kV rating of the motor. Okay, so Ki is actually this K. Okay, the Ki. Okay, so basically Ki multiplied by the armature current is supposed to give you the output torque of the motor, and Kv multiplied by the EMF. Okay, Kv multiplied by the EMF is supposed to give you the uh, omega. Okay, so basically Kv in this case is 1 over K, whatever this K here is. Okay, so just keep this in mind. They're related. They're not that different from each other. Okay, so in our case, what have we been given? We have been given ES 5 volt, right? Yeah, we have an EMF of 5 volt and we have omega of 100 RPM. Okay, this is K times 100. Okay, but this should be in radian per second. Okay, because this K and K both are in SI units. Okay, so how do we convert 100 radian RPM in radian per second? We multiply by 2 pi by 60. Okay, so essentially from here we calculate RK. Okay, so K comes out to be 5 times 3 over 10 pi, right? So basically 3 over 2 pi. Now we have been given that we want the torque to be how much? 0.5 Newton meter. 0.5 Newton meter. Okay, but this is equal to K times I of A, right? So from this equation, we can see what should be the armature current. It should be the required torque divided by K, right? That is 0.5 divided by K. Now we have already calculated this K using our back EMF measurements. Okay, and what is the K that we have calculated? That is 3 over 2 pi. Okay, so we just put that here, 3 over 2 pi. Okay, 3 and then 2 pi here. So what we get here? We get pi by 3, right? And what is pi by 3? Okay, in decimal. So 3.14, it is, yeah, you can do in your calculators, divided by 3. Okay, so it is 1.0466. You can write 6 bar. Okay, so this is essentially, you can round it off and write it as 1.047 ampere. Okay, so now what you now know is that my armature current should be equal to 1.047 ampere for the given motor, okay, for it to produce a torque of 0.5 Newton meter. Okay, so essentially now you know where both these relations came from. Okay, basically we take all the properties or the quantities that are intrinsic to the coil, okay, or the motor, and we treat it as a constant, as a single constant k. Okay, and using this we get two equations. Okay, one that relates our torque and the armature current, and one that relates our back EMF and the angular frequency, right, or angular velocity, whatever you want to say. Okay, and using these two relations, we have calculated the armature current for which the torque is this much, whatever it is specified. So you can always now the problem after this again, there can be a problem that what should be the voltage that is applied so that the armature current is this. This is the final step in the problem. Okay, but you'll learn about this when you get to motor control. Okay, right now you're just studying about the motor basics and the working of motors, how is the torque produced and all. Okay, so, but just keep that in mind. Okay, there is one more step to until you are able to actually control the motor. Okay, because you control the voltages, and those voltages in turn control your currents, and those currents control your torques, right? So I think there should be any doubt. It is like a pretty straightforward question in which we have just combined what we had studied in the above two questions. Okay, so let us move to the next question now. Okay, let me mark this as question number 4, right? So the question is, a DC motor rated for 48 volts has its armature resistance of 0.6 ohm. Okay, the speed EMF constant of the motor is 0.2 volt per radian per second. Okay, the motor drives a constant load, okay, that is independent of the speed. Okay, so the load is 2 Newton meter. Okay, so the motor has to drive it constantly, this much load. Determine the additional resistance that needs to be placed in armature circuit to operate the motor at a speed of 800 rpm, right, when it is driven by a 48 volt supply. Okay, so let me just break down the question for you a bit. Okay, so what the question wants us to do is, okay, we want the motor to drive this constant load, okay, that is 2 Newton meter, okay, at a constant speed of 800 rpm, right? So basically we want the motor, okay, to output a constant power, or specified power. Okay, And how do you calculate the power of any motor? Okay, you calculate the power as VI, right? So if you want to, you know, if you have a specified V and you want to change the power of the motor, you need to change what? You need to change the current. Okay, either you change the voltage or the current, but the voltage in this case is fixed, right? Okay, because the motor is rated for 48 volts and we have supplied 48 volts. Okay, so complete. Okay, above this, the motor will get damaged. Okay, so the only thing that we can change is our current. So how do we change the current, right? How do we change the current? So the current is change, how does current depend on? What does current depend on? It depends on voltage and the total resistance in your circuit, right? So basically you want to change the total resistance to change your current in the motor such that your net power changes. Okay, and the net power, how much you want to change such that it matches your power of the whatever power you want to output. Okay, you want to balance 2 Newton meter torque at 800 rpm. So basically tau times omega is the power, right? So you want your vi to be equal to tau omega. Okay, this is like a similar problem. Okay, so how do we do this? Okay, what is the procedure uh, for this kind of problem, right? So we have been given some quantities here, right? That the speed EMF constant is this much. And I think in your lectures, you might have seen that, your omega in this case, okay, the speed torque equation basically for a simple DC motor, okay, it is given as the supply voltage over your K. K is your, this speed EMF constant, okay, minus the total current times the torque, okay, total current times the torque, total resistance times the torque divided by K squared, right? This is the speed torque equation, okay, that you have studied in your lectures. This is the speed torque equation. Okay, so what do you guys have here? We have omega, okay, that is 800 rpm, and we can change it into radian per second. Okay, because again, this speed torque constant is given in volts per radian per second, right? By 60. So what does this become? This becomes 80 over 3 pi, right? 80 over 3 pi radian per second. Okay, this is my omega, and my V is what? My V supply voltage is given as 48 volts, right? There is no problem in this. And what is my constant? Okay, speed EMF constant, that is 0.25 voltage per radian per second, right? That is for 1 radian per second, 0.25 volts back EMF is generated. Okay, no problem till this. And what is the load that you want to support? That is 2 Newton meters, right? And what is R? R is your R total. Cool. So now again, I told you, right? You want to modulate the current, and to modulate the current, the only choice that you have is to change the resistance. Okay, the only choice that you have is to change the resistance. Okay, because you cannot change the supply voltage. Okay, because it is fixed. And if you try to increase, basically it is fixed. So that is why you can change the supply voltage. So that is why you change the current, okay, of the, the total current of the circuit. Okay, and how do you change? So you add a series resistance. Okay, so one is your, we will see, like, you have your armature current, right? You have your armature current given as 0.6 ohm. Okay, so this is 0.6 ohm. Now, if your R total from this equation that we'll calculate, it comes out to be greater than RA, then of course we know that we need to add an R in series. Okay, and if it is less than RA, okay, then we know that we need to add a resistance in parallel. Okay, like as simple as that. So we put everything that we have here, all these values in this equation, and we get the value of total resistance. Okay, so if you put the values here and you know do all the calculations, you will find out that R comes out to be 3.382 ohm. You just have to put everything here and then just do the calculations. So now you see that this total resistance, this is your R total. Total resistance is greater than your armature resistance. So basically, you need some extra resistance that is in series with armature, right? And how much is that? This is your total resistance equal to your armature resistance plus some, let us say, Re, that is extra resistance. So your Re is, let me call this RT, R total, RT minus Ra, right? And this is 3.382 minus 0.6 ohms. Okay, this is the extra resistance that I need. So finally, what I get is 2.782 ohms. Okay, so this much resistance I need to add extra in series with my motor, okay, in the circuit basically, to satisfy these conditions. Okay, what are the conditions? To support a load of 2 Newton meters at an RPM of 800. To maintain this RPM of 800 RPM, I need to add this much resistance. Okay, so basically, as I explained again, explained previously also, what we are trying to do here is we are trying to match the power of the motor to the power required at the load end. And what is the power required at the load end? The torque delivered by the motor to balance out the load multiplied by the speed of the motor or the motor shaft. Okay, so tau times omega gives you the power, output power that is required. And how is the power generated inside the motor? Okay, so power in a simple electric circuit is given by what? The voltage times the current of the circuit. And since you need to change the power of the circuit, you need to change either the voltage or the current of the circuit. Okay, source voltage or the net current, but you cannot change the source voltage here. Okay, because you cannot, you know, plug, take the battery out and plug in a new battery, right? You have your source fixed. Okay, so the only way for you to change the power is to change current. And how do you change current? Okay, so basically current, it depends on your voltage and your total resistance, right? Total resistance of the circuit. Now we have discussed already, we cannot change the voltage, right? So that is why we change the resistance. Okay, and like how we change the resistance, we saw here. Okay, that we either, if the total resistance is greater than the existing resistance of the circuit. Right now, the only existing resistance was the armature resistance. Okay, but if the total calculator resistance is greater than the existing resistance, then we need to add an extra resistance in series in the circuit. And if the total resistance is less than the existing resistance, then we need to add a resistance in parallel to the second. Okay, like that is the only thing that you need to remember. That is that is it. Okay. So I think that these four questions would give you like a good view of all the kind of concepts related to a DC motor. Okay, like related to the torque generation, related to power, power output of a DC motor, right? And all the expressions that we have used, in all the four questions, they are from your lectures. Okay, so if you want to see, the derivation of these, you can just watch the lectures, or I think you might have done the derivation in your high school also, right? So I think this is more than enough for this week's lectures. Uh, I will end the meeting. Thank you.